Good. Yeah, they come in here every day and just like they don't ever stop talking. Between the five of them, it's just a constant wall of noise.
What's a raisin brand to like African like warlords?
Yeah, they talk about everything and like you can try to get them to be. I try to get them to be quiet, and it doesn't work all that often. I do. They drag me in. Because let's be honest, like who doesn't want to get on a Raisin Bran conversation? You know, they're like, what's your favorite cereal? And as an adult, you can't just be like, yeah, you know, no. Well, I do eat Cheerios. I ate Cheerios this morning. Honey Nut, but when you look at the package, Honey Nut Cheerios has a lot of sugar in it. Well, but you gotta. I mean, I gotta think about my health. I don't wanna die at like the age of 50 or 60 or something. So I've been doing regular Cheerios, no Honey Nut, no like putting spoonfuls of sugar on it. And it took a little while because the first couple bowls I'm like, this is trash. But it's all right. It's not too bad. But like if diabetes wasn't a thing, Cinnamon Toast Crunch, like all day long, every day, every meal, Cinnamon Toast Crunch. I like this. Everybody loves pizza. Guys.
No.
What? No. Marshmallow cereal, like no. Anything with marshmallows, no. No. Yeah, no. That's not. You're not improving now. You want to have marshmallows? The only place marshmallows belongs is in hot cocoa or on s'mores. That's it. That's it. And other than that, you shouldn't be eating marshmallows.
What about just straight up marshmallows?
No. There's a million cereals I'd eat before I eat Lucky Charms. Come on. And the people, like, if anybody watches this video at home, they're gonna be like, "What is going on here? Like, this is supposed to be the chemistry video, and they're talking about cereals." All right. So I'm on freeze. Let me unfreeze this. We're gonna have a pretty quick assignment today. We're talking about electrons. Everybody close your Chromebooks. Let me go to full screen. No, this is not what I wanted. Why is this PDF? Here we go. Nope. Electron configurations. Where's my other PowerPoint?
Yeah.
Hold on a second. Let me see something. That was not what was supposed to happen. Chemistry. Because we went all the way through the other PowerPoint the other day, right? Pretty sure we did.
We did? Oh, yeah, we did.
Electron configurations 3.4. That's a PDF. Okay, hold on a second. Let me double check because if there is a PowerPoint, I want to be able to use it. If not, I'll just have to do the whole thing on the board, which isn't that bad. Why is this happening? Hold on. I know they're like, what is happening here?
He's gonna have to take him.
Okay.
That's so ugly.
Y'all still have the black one?
No, they changed it from mine.
Yeah, they changed it to gold. Yeah.
Y'all's must not have updated.
It's gold. It's gold. What they get on websites.
That is not
All
gold. That is burnt.
All right. So let's see. So come on here. Let's see. We're gonna open up this. We're gonna go to the teacher stuff that y'all don't have over here on the side. Additional resources. Lessons by chapter. I think it's going to be the lessons, the PowerPoints, and we're in chapter 3. And we have a zip. Download it. Open it up. And now we're open. And no, that's it. All right. So let me double check this real quick. I clicked that a bunch apparently. But I'm pretty sure, no, that this didn't have it in here. Don't worry, we got plenty of time. Electron configurations. No. That's it. All right, so let's just do it this way, okay? I'm gonna hit big screen here. What we're talking about today is Lewis dot structures. And Lewis dot structures is a different way to talk about electrons and to basically show your electrons without having to do all of the electron configuration stuff. So no letters, no numbers. Well, there are letters for the elements, but it's going to be pretty easy. The trick about Lewis dot structures is it only works for the really simple stuff. So anything in the D block, not happening. Anything in the F block, it doesn't work. The only thing Lewis dot structures works for is the S block and the P block. And now, real quick, how many electrons are in the S block? How many electrons are in the P block? 6. What's 2 plus 6? 8. And so for simple elements, there's an idea of this rule that's called the octet rule. That's so disappointing. Trash. So it's called the octet rule. What does oct stand for?
8.
8. So octopus has 8. October is October the 8th month.
I have no clue.
So why is October the 10th month when oct means 8? It's because we used to only have 10 months, and then we added 2 months, and we named them after Roman people. Julius Caesar gave us July, and Augustus gave us August, which is why October is not the 8th month. December, which dec is 10, like a decathlon, or a decade is 10 years. December should be the 10th month, but it's not. It's the 12th month. That's a little history lesson for you. So oct is 8, and it's the octet rule, which basically states that on the outer shell of electrons, so think about this as kind of like an onion. You have all these different little shells of electrons. This is not how electrons actually work, but it works for our visualization. You have the nucleus in the center, and you have your different energy level shells. And when another atom comes around and wants to bond with your atom, it's not the inner shells that match up, it's the outer shells. So what's most important for how your atom is going to chemically combine and do chemical reactions is what's on the outside of that outer shell. And the idea here is all elements except for hydrogen and helium want to have 8 electrons on the outside shell, as long as they're not in the D block and as long as they're not in the F block. This only works for the S and the P block. So they want 8 electrons around here on the outer shell. If they have 8 electrons, their wallet's full. The bank account's flush. They don't need no friends. They don't need to talk to nobody. I'm good. I'm done. If they have less than 8 electrons, that's what they want to get more electrons. Or if they're closer down to 0, they might want to get rid of some electrons, and then they get rid of the outside layer, and the next layer underneath it has 8. And so they always want to get to 8. Sometimes they go up to 8. Sometimes they go down to 0, which essentially gives them to the last level, which should be full with 8. So all the time you want to get to 8 electrons. And the idea here is you can literally just count the rows. Let me bring my video back over here so the online people aren't like, man, I watched Serial and then you just walked away from the video. I don't even get to see nothing. So you literally just count the rows. If your element is in the first row, on your periodic table, it's the orange, lithium, sodium, potassium, rubidium. Those are going to have 1 electron. So literally have 1 electron in the outer shell. If you go to the second row or second column, beryllium, magnesium, calcium, strontium, those are going to have 2 electrons in the outer shell. You skip over the D block because the D block does not count for this. Things get weird in there. They don't follow this rule. You go to the next column, and the first column in the P block. Boron, aluminum, gallium, what is that, indium? That's going to have 3. Then you go to the next one. Carbon, silicon, germanium, what's SA? 10. Oh, yes, SN, 10. That's going to have 4. Nitrogen column will have 5. Oxygen column will have 6. Fluorine column will have 7. And then the noble gases at the very end will have 8. It's really easy to find an element, count over 1, 2, 3, 4, 5. Phosphorus has 5 electrons. I know that it has 5. Now, how do you draw this? Essentially, you're going to take your element. You draw the symbol for it. So somebody give me an element in the P block.
Bromine.
Bromine, over here, right underneath chlorine. What column, how many electrons is it going to have?
7.
It's going to have 7, not 8. It's almost to 8, but it's not quite to 8 yet. And so bromine is going to have 7 electrons. How do I draw this as a Lewis dot structure or a Lewis dot diagram? I give the symbol, bromine, big B, little r, and I literally just start to put dots around it. Now, here's the thing. We talked earlier about the, I think it was the Hund's rule, maybe, that electrons are all negative. You weren't here yesterday, but electrons are all negative, but you were here the day before, so you should know about the Hund's rule. They're all negative. They're not going to want to sit next to each other. So I related the electrons to students in the seats. If you get a chance to sit in a seat that doesn't have nobody next to you, you're going to do that. Electrons are going to do the same thing. So I need to draw 7 electrons around here, but they got to be spaced out. Now, you can't have any in diagonals. It's either going to be top, bottom, left, or right. So the maximum I could have is 8. How I'm going to draw this, start at the top. 1. Go clockwise. 2, 3, 4. So notice when I get to 4, they're all spread out. I don't have any pairs. But now all the free seats are taken up. I need to get up to 7. I need to start doubling them up. So I'm going to go back to the top, add a second one. That's 5, 6, and 7. So now I have 7 electrons. I have 3 pairs here and 1 single electron. Now here's the thing. Bromine is really close to 8, right? And everything wants to be at 8. They work really hard to get those extra electrons to be at 8. So bromine at 7 is going to be really good at stealing electrons from other atoms. If it bumps into some other atom, like oxygen or carbon or whatever, it's just going to take one of those electrons. It's going to take it with it. It's like, this is mine now. I now have 8 electrons, and I'm perfect. And so it's going to be really good at stealing electrons. This is the electron that has an open spot. So notice that both of these seats are full. These electrons in these doubled up seats are happy where they're at. What we call these are non-bonding electrons. And I'm still just really surprised that I don't have a PowerPoint for this. But these are called non-bonding electrons because they're already paired up. They don't have anything to do. They don't need any other partners. They're good like they are. If you have one by itself without another partner right next to it, that's called a bonding electron. So non-bonding is the pairs. Bonding electrons are the single ones. So let's do another one. Let's say I have nitrogen. Nitrogen has how many electrons?
5.
It has 5. So I'm going to do 1, 2, 3, 4, and I need one more. So I have 5. So how many non-bonding pairs does nitrogen have?
1.
Just the one, non-bonding. Non-bonding is going to be the one pair here. And how many bonding electrons does it have? 3. So actually, nitrogen can form a bond with 3 other electrons. Bromine over here only has 1 of them. It can only form a bond with 1 other atom. And so bromine will never be like the center of attention. It's always going to be off to the side on the outside because it can only have 1 thing connected to it. Where nitrogen can be like the middle spoke of like a wheel, or the middle hub of a wheel, and have stuff kind of all around it and be right in the middle. So the more bonding electrons you have, the more bonds you can have. And, you know, this is actually how we figure out how atoms build themselves and connect to each other. So, for example, let me show you. Let's take a common chemical like H2O, water. We're going to figure out how water bonds together and what's happening there. So H2O, how many do I have and what do I have them of? 2 hydrogen and 1 oxygen. So I have H2O. The 2 goes for the hydrogen and I have 1 oxygen. Let's start with the oxygen. How many electrons does oxygen have? It has 6. So it's going to have 6 valence electrons. Now it has more than 6 total electrons, but we're just talking about valence electrons, which means the outside. This is the word. Valence electrons. That means your outside shell of electrons. So oxygen has 6. I'm going to do 1, 2, 3, 4, 5, 6. So How many non-bonding pairs does it have? 2. How many bonding electrons does it have? 2. Now, how many atoms do I need to hook up to oxygen to make water? 2 hydrogen. So I got a place here and a place here. Now watch what happens. Hydrogen is a little different. Does hydrogen have does hydrogen have any p elements in it? No. So it can't have 8. Same thing with helium. Hydrogen and helium only have an S level, so they can at maximum have 2. So they don't really fit in the octet rule, but we still kind of use them to build elements. So hydrogen and helium only have 2. Remember that they'll never get up to 8. So hydrogen has how many electrons with it? Just 1. So I have a hydrogen here and a hydrogen here with 1 electron. Now, what's going to happen, and we haven't gotten into bonding quite yet, we're going to have a covalent bond here. These electrons are actually going to share in between these atoms. So I'm going to draw a bond right in between them. And they might ask you to do this a little bit. I'm going to draw a bond right in between them. Now, if we consider these to be shared, how many electrons does hydrogen have now? 2, and that's its maximum. Now hydrogen's happy. It's got both electrons in the S shell. That shell is filled up. It's good to go. This hydrogen also has 2. It's got the one here and the one that it came with. So it's sharing those. Oxygen now has how many? 1, 2, 3, 4, 5, 6, 7, 8. So now oxygen is filled up and it's satisfying that octet rule. It has all 8 electrons. And this is actually the shape of what a hydrogen or a water atom looks like. It has this kind of bent shape in it. And the reason is these 2 electrons over here are more negative. And this area over here, because it has less electrons over this entire area, is more positive. And so what you have with water is this negative end and this positive end. And let's be honest, oxygen's a bigger element. It has more electrons. They're playing video games at oxygen's house. And is hydrogen really going to get all the turns playing the Xbox? No. Oxygen's gonna be kind of the bully here. They're not a bully, but it's not gonna let hydrogen play with the electrons all the time. So these electrons, while they're shared, most of the time they're over in oxygen's house, and the hydrogen just gets to use them sometimes. So the oxygen actually hogs most of the electrons. It stays more negative. The hydrogen stays more positive, and that makes it a polar substance, which is why water clings together and stays like in those little droplets, or why we have a meniscus and it kind of curves up on the sides. That's what that polar kind of substance does. If it's non-polar, it's not going to do that. It's not going to try to cling together. You're not going to have any surface tension of your substance. And so I don't really know what kind of questions they're about to ask you on here. But remember the way we draw it. You start at the top, you go clockwise and add your dots. You do 1 at a time. And if you need to add more, then you start to double up from the top going clockwise. So go ahead and open the assignment. And actually, I'm going to pull it up too with you. And let's see what we got going on with it. I really need to figure out what I need to find a PowerPoint for that. And you'll need to use your periodic table for this. Let's see. So this first one, oh wait, hold on. You need to see all the answers. The first one's just going to ask you, find the elements, how many valence electrons do they have? So you look on the periodic table, figure out what the number of outside valence electrons is, and fill that in. Not too bad. Not too bad. Okay, everybody look at this one real quick. I just want to explain this. I think you can do the first 3 pretty easily. This one has how many electrons? It's got 5. So that tells you it's in a specific column on the periodic table. It's got to be in the 5th column. So you count over 5 columns, skip the D block. 1, 2 in the S block, 3, 4, 5. So it should be the 3rd column in the P block. Only one of these answer choices is going to be in that column where it could possibly have 5 electrons. And so that should help you out. Does that make sense for everybody? Yeah, so you know it has 5. You don't know what element it is. They're asking you what element it could be, because I don't think there's an element X. Same thing here with 3. This one's 8, so it's got to be a noble gas. But remember, helium can't have 8. It's got to have 2. Yep. And so you skip the D part. You don't use the pink ones. Just the yellow and orange, and then D6 over here. So you go from left to right. Yeah, so this shouldn't be too bad. Whenever you get done with this, if you want me to open up the assignment from yesterday, I will open it up for you. Just let me know. Or if you're at home, email me. Hopefully this explained a couple things. We'll get more into this when we get into bonding. I guess I jumped the gun showing y'all how we do bonding, because we'll get to that later. But at least it's introduced. So yeah. If you have questions, send me a screenshot or let me know and I'll help you out.
Can you check